Hey everybody, this is Lucas Bennett, and this is my lab number 8. So today we'll be looking at a problem where a star is rotating around a black hole, and we need to find out what the black hole's mass is. We've been given the star's positions over 25 years, and we get a new position every day out of those 25 years. We get the star's mass, we get the black hole's position, and with these we're going to use a VPython program to simulate this system and to calculate the mass of the black hole. So the equations that we'll be using to help us figure this stuff out will be the momentum equation, which is delta P equals F delta T, and we'll be using the gravitational formula, which is F equals G m1 m2 over r squared. And these will help us to figure out the black hole's mass. So to help us visualize this, I made a little drawing. We're going to start with this one. Or let's start with this one. So basically, this is the star, and this is the black hole, and these are the two. We're going to split the force up into two components: the F-net parallel and the F-net perpendicular vector. Let me draw this in a little better. Sorry. Okay, and if you add these two vectors together, and by the way, they're called parallel and perpendicular because the parallel, for example, is parallel to the momentum vector, and the perpendicular is perpendicular to the momentum vector. So if you add these two vectors together, this vector is equivalent to this vector. I mean, not really, but it is in real life. You'll get the resultant vector, if you do it tip to tail, of the actual net force vector, and that is what we're going to help us use to find the mass of this black hole. Okay, so alright, that's a little later. So in the VPython program, I set the star's mass equal to the 1.989 E30. I set the change in time equal to 1 day in seconds because it updates every day. And this is where we're going to load in all the position data from it. There's a file, the CSV file right here. This has all of the positions over the 25 years for every day of the star. So that's going to load into this array right here, and then we'll use it to calculate all our different values. Okay, so here's pretty much everything. And yeah, and so in this final equation, two things that I'm going to print out, I have the magnitude of the force times the basically the r in this equation right here. It's just the magnitude of the r vector squared over big G times the mass of the star, and this is going to give us the mass of the black hole, so that'll print out. And also I have this is the number of Earth years that we will be this is going to print out how many Earth years we looked at over the time interval. So when we run this code, boom. And that arrow right there is actually the net force parallel vector. And so as it's going around, this shows the magnitude and the direction of that vector. And basically, for the parallel and the net force, you can basically come back to this. So this was that vector that we just saw right here. This is the perpendicular vector, and this would be the net force just combined vector. So that's what those look like in the VPython program. So then basically the what if question was if the black hole was replaced by a different black hole. We'll go down here. So the new one is this green one. Could we predict, but every other number in the problem stay the same, could we predict a different mass for the black hole? And I'm going to say no, because if all of the numbers stay the same, then we can't predict anything new because all we have about the star is its position. And so if the position stays the same and this star continues to revolve around the black hole the same way, we can't do anything else with that. We can only calculate one mass, and that's the mass that we already have. So we can't calculate a new mass for that. Also, one of the questions is, how is dPdt and Fnet related? And they are related through the momentum equation up here. So basically, F just equals delta P over delta T. So really they equal each other. But in our situation, in the VPython program, they do differ because delta T is not approaching 0, which we would like it to be. And to find the true Fnet, we would have to take the derivative. We would have to take a derivative, so we would get an exact value. But right here, we're gonna have some value over some value, and they're both not approaching 0. So it's more of an average change rather than an instantaneous change. So Fnet is perfect, whereas delta P over delta T is not perfect. So that's the difference in that. And the same thing goes for Fnet parallel and Fnet perpendicular and delta P over delta T parallel and perpendicular. They're just different because they're not exact values. So I think that's my lab. Thank you.